What I would like to cover in this chapter are a few short examples on how to go about calculating acceleration constraints when ropes and pulleys are involved. For the first example, let's just review the simple scenario where we have a pulley held from ceiling, and then we have a rope that goes over it. We have mass m1 on one side and mass m2 on the other side. Now, in this simple scenario, it is fairly obvious that if we call the distance from the pulley to mass m1 y1 and the distance from the pulley to mass m2 y2, then it's fairly clear that y1 plus y2 is equal to the length of the rope. So if this is pulley, the length of the rope, so y1 is equal to L minus y2. If you were to differentiate this expression, we end up with dy1 dt is equal to L is constant because it's the length of the rope minus dy2 dt. Differentiating one more time, we end up with actually, before we differentiate, let me just say what dy1 dt is. dy1 dt is the velocity by which mass 1 is moving, so that's equal to velocity by which mass 2 is moving. And then differentiating one more time, d by dt, we of course end up with a1 is equal to minus a2. This is just a simple scenario which says, illustrates how one would go about treating more complicated configurations. So here y1 would have an acceleration a1 and m2 would have an acceleration a2, and they're opposite in sign, of course, equal in magnitude but opposite in sign. Now if we consider the next example, so let's consider an example where we have once again a pulley, this time a big pulley like this. Let's call this pulley A, held from the ceiling, and then we have another pulley B here, and once again let's have our masses M1 and M2 attached to the two pulleys. Now let me use the blue pen to show the distances. So we have, if I call this y1, and then the distance from the pulley to mass m2 y2 on this side and y3 on this side. Now I can write the by the way, the distance from pulley B, so this is pulley B, this little distance here, let's just call it delta y. It's just a fixed length of the hook from the pulley to the mass. Now you see that y1 plus y2 minus delta y plus y3 minus delta y must equal the length of the rope, the total length of the rope, because it's one continuous rope that we have. So y1 is equal to L plus 2 delta y, y2 delta, I'm taking 2 delta y to the other side, minus y2 minus y3. Differentiating with respect to time, we end up with dy1 dt is equal to 0 minus dy2 dt minus dy3 dt, and differentiating one more time, we have dy1 d2y dt squared actually this is not, you're probably not done this yet, so let me just show it as differentiating one more time with respect to time, of course we end up with a1, which is the acceleration, that's the rate of change of velocity, which is equal to minus a2 minus a3, and a1 and a3 refer to the acceleration of mass m2. So this is a2 is equal to a3, let's just make it equal to a, and a1 is the acceleration of mass m1, so this is a1. So from here you see that a1 is equal to minus 2 to a2, which is equal to minus 2 a3, and since the magnitude, we can call a2 or a3 equal to a, so you end up with a1 is equal to minus 2a, so that's a right there. So you see that the mass m2 is now accelerating downwards at half the magnitude that mass m1 is accelerating upwards. So just two simple examples on how to treat cases when, or you have to work out the acceleration constraint when you have pulleys and strings involved. We've done cases where we had, let's say, an object m1 sliding on, in this case, a frictionless surface, we call it, and if we have a scenario where this is attached to a pulley, it's attached to a wall right there, ropes comes around, another pulley, and here we have m2. Now you can do a similar analysis and figure out that m2, this is a2, that a2 would be equal to twice, oops, I'm sorry, this is a1 up here, twice a1. There's also a negative sign, so this is the magnitude would be twice a1, but if you were to choose your coordinates like this for m2, then of course a2 would equal minus 2a1, since a1 is towards the positive of x and a2 is towards negative of the y-axis. Alright, let me do, well actually let me ask you this quick question here. Let's say we have a pulley hanging from a ceiling, and then we have two masses, m1 and m2, where, well actually I'm gonna do three different scenarios. So let us work out what is the tension, what is the force that this blue rope exerts on the ceiling. What is that force? So you're interested in figuring out what is that force when three cases, m1 is equal to m2, m1 is less than m2, and I'll give you two other scenarios in just a second. So if m1 is equal to m2, let's work out this scenario first. Let's identify the forces acting on m1. We have tension there, we have m1g down this way. Forces on m2 are of course tension again, and m2g. Similarly on our pulley we have a tension there and a tension there. We have to also acting on the pulley in the upward direction. There's I'm gonna call it T0, which is the tension in the rope applying an upward force on the pulley. And Newton's third law says that the force that the rope applies to the ceiling is an action-reaction pair, of course, with the force that I'm sorry, let me take that back. The force F that we're trying to figure out and the T naught are of course equal in magnitude because we are dealing with a massless string there. So in case of M1 equals M2, if you do a free body diagram for M1, we end up with T is equal to M1G because we have an equilibrium situation where A is 0. We also end up with T is equal to M2G, looking at mass M2. And so we have a case where and looking at our pulley, we have T naught is equal to 2T. That's true in all three scenarios, in all the scenarios that we're going to consider. So we looking at these, we end up with T naught is equal to twice M1G, which is also equal to twice M2G. So T naught is simply twice mg, where m is either m1 or m2, of course. So that's an obvious solution. If there is no acceleration in the system, if the system is in equilibrium, then the tension by the rope on the pulley is equal to the total weight of the hanging masses, which of course also tells us that F is equal to 2mg in magnitude. Okay. Now, what if M1 is not equal to M2? What if that's the case? If let's say M1 is less than M2, right? If M1 is less than A2, then M1 will be accelerating up that way, A1, and M2 will be accelerating down this way. That's A2. Our acceleration constraint consideration tells us that A1 is equal to minus A2. So we can call this minus A for M1 and I'm sorry, plus A for M1 and minus A for M2. Now, doing our free body diagram and Newton's second law application gave for M1, we end up with T minus M1G is equal to M1A. For mass 2, we have T minus M2G is equal to minus M2A. And substituting for T, we have actually let's work out an expression for T. So we have T is equal, actually no, I'm sorry, let's figure out A first. Let's figure out A. So A is equal to what do we have here? T minus M1G divided by M1, and then substituting this A in our second expression here, we have tension is equal to minus M2 times A, which is T minus M1G divided by M1 plus M2G. So our tension is equal to minus M2T minus plus M2G plus M2G, which is equal to, no, I made a mistake. Let me erase that and do my algebra one more time. I have minus M2 into T minus M1 minus a G plus M2G, which is equal to minus M2T divided by M1 minus plus M2G plus 2M2G. Alright. So you see that if we have a case, and by the way, this is T, and once again considering the upper pulley, we have T naught is equal to twice T, because if you remember in the upper pulley we had tension down, and T naught up. So T naught, which is equal to F in magnitude, is equal to twice that. So we have minus 2 m2 Let us now consider scenario where we have a pulley hanging from the ceiling and we have, let's say, a 1 kilogram mass on one side and a 3 kilogram mass hanging on the other side. Now, if you're interested in figuring out, let's say, this tension here, T naught, being applied to the pulley by the upper rope, how do we go about doing that? Well, obviously this is the 3 kilogram weight is greater than the 1 kilogram weight, so we will have an acceleration in the system, A this way and A that way. So the forces on our 1 kilogram mass are 1 kilogram times G, so this is just G newtons this way, and tension up this way. Similarly, we have T up that way, and we have 3G newtons down this way. Now the forces on the pulley, we have tension down, and T naught up. So you see that T naught minus 2T is equal to 0 because the pulley is in equilibrium, which says T naught is equal to 2T. So our job now is to figure out what T is. Looking at object of the 1 kilogram mass, we have tension minus G is equal to mass is 1 kilogram, so that's simply A. And looking at the 3 kilogram object, we have T minus 3G is equal to minus 3A because our mass is 3 kilograms and acceleration is negative A. So in this, from a first equation we have, if we substitute for A from first equation to second equation, we have tension is equal to 3G minus 3A, which is negative 3 into T minus G, which is equal to which is equal to 3G minus 3T minus 3G plus 3G, I'm sorry, which is equal to 6G, and this becomes 4T. So 4T is equal to 6G, or tension is equal to 3 over 2G. If tension is 3 over 2G, that means T naught is equal to 6 over 2, twice that. So 6 over 2, which is 3G newtons. So we have a T naught is equal to 3G newtons. So notice that T naught, in the first look, one would have guessed that, well, if the weight of this mass is G newtons and the weight of this mass is 3G newtons, so to put the T naught is supporting a total of 4G newtons. Without going through this analysis, one might have guessed T naught is equal to 4G newtons, but in fact, because the two masses are accelerating, the total mass, the T naught is less than the entire mass. Now you can extend this analysis and kind of basically say that, okay, what if we were to apply a force downwards here, I'm gonna call it F, onto my 1 kilogram mass. such that the 1 kilogram mass and the 3 kilogram mass are in equilibrium. What then? Well, to figure that out, once again do your free body diagram. For the 1 kilogram mass, we have tension upwards minus F minus G is equal to, in this case, 0, because acceleration is 0 for the 1 kilogram mass. And looking at the 3 kilogram mass, we have tension minus 3G, that's equal to 0 as well. So from these two equations, we obtain that tension, let me see, tension is equal to 2G, I believe, right? Tension, actual force F, I can write that. Force is equal to, if I subtract the two equations, I end up with force is equal to 2G newtons. So if F is equal to 2G newtons, that means that tension is equal to 2G 3G newtons, which in turn means that T naught is equal to 6G newtons. So if you had a force F pulling down on mass, the 1 kilogram mass, then T naught, the tension in the upper rope, would equal 6G newtons, whereas when the two masses were accelerating, of course, it equaled only 3G newtons. Now if I switch the color of my pen, and basically now let's say that I don't have this force here, but instead I apply a force upwards onto my 3 kilogram mass F. What then? Well, to figure this out, I'm going to use this corner. I apologize for being stingy with space, but I want to keep the diagram in view. So for the 1 kilogram mass, we simply have T minus G is equal to 0, equilibrium. For the second mass, we have T plus F minus 3G is equal to 0. And from these two equations, you can obtain F. F is equal to, so you have T is equal to 2G once again, 2G newtons. So the tension in this case becomes tension, substituting in our equation, tension becomes T is equal to 2G. T becomes G newtons, which means that T naught, which is twice T, is equal to 2G newtons. So notice that if we were keeping the system in equilibrium by applying a force on the 3 kilogram mass, then T naught would only be, T naught, which is up here, would only be 2G newtons. If we held the system in equilibrium by applying a downward force onto the 1 kilogram mass, T naught would be 6 newtons, 6G newtons rather. And if we let go and let the system do what it does, which is accelerate, then T naught would be 3G newtons. So I wanted to go through these examples to basically highlight the importance of being systematic in your analysis when you consider acceleration constraints, and in particular systems which are not in equilibrium, which are accelerating.